Okay, so the flame you can see on the left, you can just barely see. It's really, oh, there it is. Really red. That is a strontium chloride solution. And there was a much smaller one on the right that was purple. And it went out really fast and was uneventful, so I'm not going to redo it. So what we're going to see is we're going to see what creates that bright color. How can you tell what color of light you're going to see when you excite an electron and it falls back down? So the energy is going to be given off when the electron falls back down. So every element, I pointed out that that was strontium, every element produces its own colors. In fact, it produces its own series of energies that it's giving off. And it's kind of its fingerprint. We can look at stars and we can see the bright line emission, or the fingerprint that they produced, by seeing what electromagnetic radiation those stars are giving off. So bright line emission is the emission that's given off when excited electrons fall back down to the ground state. And they give off energy as they make that fall. The ground state is the lowest energy level that electrons can occupy. That's how we've been writing all of our electron configurations or orbital box diagrams. We've been following off-bow and filling from the lowest to the highest. So the absolute lowest place you can put the electrons, that's ground state. Excited is when electrons have skipped off-bow, so they've broken it. They've been excited and pushed up to a higher potential energy. And I just did that by adding heat to that solution, to the atoms in that solution. You can add electricity. There's other ways to excite electrons. So you're adding energy, which promotes them to a higher potential energy. And then as they relax and they come back down to a lower energy level, that change in potential energy is given off in the form of electromagnetic radiation. And like that radiation, that one was, some of it was red, so we could see it. We can actually figure out, like what kind of radiation is going to be given off. Electromagnetic radiation, will we be able to see it or not? So what's happening is we excite an electron from a lower state up to some higher state, and then with time, that electron falls back down to some other lower state. I'm going to make mine go from the first up to the third and come back down to the second. Or it could fall all the way back down to the first. So what's happening is as that electron falls, energy is going to be given off. And the amount of energy given off is going to correspond with the change in potential energy. So this would be less energy given off than this guy. So let's look at, the proof we had, strontium, and unfortunately, the potassium it went out before I turned the camera on. The strontium was bright red, so the energy given off when electrons were falling from higher to lower energy levels corresponded with the energy of red light. This one gives off purple light, a little bit higher energy, but sorry, show you some other time. So we can actually calculate what is the energy of the electromagnetic radiation that's coming off, and can we see it or can we not for a hydrogen atom? It's a little specific. So what we're going to do is we're going to try it out. There's an equation on your gravy sheet, and it is a way of calculating the energy at any principal energy level. So at any energy level, this is the principal quantum number, n. So the energy is always going to equal negative 2.178 times 10 to the negative 18th joules, and that is divided by the energy level squared. So we're going to see what happens when an electron goes from the second energy level down to the first. It's going to be giving off, it's going to be giving off energy as it loses potential energy, going from the second energy level to the first. So we want to find what that change is. So we'll need the energy of the first level, the energy of the second level, and then change is always final minus initial. So the change is going to be the energy of the first, that's where it ended up, first, minus the second, where it started from. So the first thing I do is I'm going to find out what is the energy of that first level. So negative 2.178 times 10 to the negative 18th joules. I plug in the principal quantum number, energy level 1 squared. So this is easy. Energy of the first level is just negative 2.18 times 178 times 10 to the negative 18th joules. And what that means is that is the amount of energy it would take to remove an electron from that first shell. So this thing it's missing 2.178 times to the negative 18th joules to have an electron removed. So that's the first level. Let's find the energy at the second level. That's going to be negative 2.178 times 10 to the negative 18th joules divided by n squared. In this case, it's 2, so 2 squared. And that one ends up as a negative 5.445 times 10 to the negative 19th joules. So it's a smaller amount to the negative 19th instead of the negative 18th. And that makes sense, because now it's the amount of energy required to remove an electron from the second shell. It's easier to remove an electron that's farther away from the nucleus because it's less attracted to the nucleus, right? If you have two magnets and you're separating them from close up, it takes more energy than if you're separating them from farther away. Okay, so now I have the energy of each level, the first and the second. I'll go ahead and subtract the second from the first, and I'll get that the change of energy is 1.634 times 10 to the negative 18th joules. All right, and it's negative. That's the change of energy was negative. Energy was lost. But now I'm going to stop talking about it as negative, because now I'm saying, so about that energy that was lost, what is the frequency of that energy? So, you know, one thing gains, another thing loses. I could say, well, the potential energy was a loss of that, and the light given off is going to be energy of that amount. So that's my energy. I'm going to use the Gregg sheet again, and because I'm trying to find out, we said, what will this electromagnetic radiation look like? Will we be able to see it or not? So we've got the energy of the radiation. We need to know what the wavelength is. So I can use the equation that E equals Planck's constant times frequency, and then using frequency I can get wavelength. So I have the energy. H is Planck's constant. It's given on the Gregg sheet, and that nu is going to be our frequency, and that's what we're going to solve for. So I'm going to rearrange so frequency is by itself, divide both sides by Planck's constant. So frequency is equal to the energy divided by Planck's constant, and that ends up being 1.634 times 10 to the negative 18th joules all over 6.63 times 10 to the negative 34th joules times seconds. So that's the constant I just took from this sheet. So I got seconds divided by seconds. Oh no, sorry, joules, that's a J. Whoops. I got joules divided by joules, and that gives me 1 over second for my unit. So per second is good, because it's how many times does a wave, the frequency, that's what I'm solving for, is how many times does a wave pass a point in a given amount of time. So there's going to be a certain amount of cycles per second. How many waves pass per second? So I just go ahead and divide, and I got 2.46 times 10 to the 15th cycles per second. Okay, so that's the frequency. Now that I have the frequency, I can see that the speed of light is equal to the wavelength times the frequency. That's also taken straight off your Gregg sheet. It's all in the atomic structure section. So now, this is a constant speed of light. Always travels the same speed in a vacuum. And this is the frequency we just solved for. I'm going to solve for the wavelength so I can look on the electromagnetic spectrum and see what this light would look like. So I'm going to get wavelength alone by dividing both sides by frequency. So wavelength is speed of light over frequency. That's 3.0 times 10 to the 8th meters per second is the speed, divided by 2.46 times 10 to the 15th cycles per second. So I've got 1 over second divided by, or meters per second, so per second divided by per second. I'm left measuring length in meters, and that would be a good unit for length. So then I'm going to take this divided by this, and I get that I have 1.2 times 10 to the negative 7th meters. Okay, so the visible spectrum that I want to compare this wavelength to and see if this is visible light or not is from 340 to, 380. 380, right? Yes, 380 to 740 nanometers. That's the visible spectrum. So I'm going to convert those meters to nanometers, also just because I like to do that. So here, we'll just go on next. So 1.2 times 10 to the negative 7th meters. I want nanometers, so I'm going from meters to nanometers. If I had a meter, I would have 1 times 10 to the 9th nanometers because they're super small. So I'm moving the decimal 7 times this way and then 9 times that way, so basically 2 times that way. So I get 120 nanometers. So that's not going to fall between my 380 and 740. The wavelength is too small, which means the frequency is too big. So we saw this, and C is a constant. As this gets smaller, this gets bigger. So the frequency is too big. And since energy equals a constant times frequency, it means that was too big of a jump. It was too big of a fall. The electrons are falling too great of a distance to actually be seen. And that is actually how the energy levels go. It's this great jump and then a smaller one right there. And then it gets smaller and smaller and smaller. So this jump right here is too large to be seen, so it must be somewhere else. And I'll tell you, the Balmer series is the series of falls that does create visible light in the hydrogen atom, and that's when you're falling to the second energy level. So anything falling to the second energy level is about, well, not anything, but many of those falls are going to be visible. That's what makes the visible light. The end.